The substitution rule. This is a critical technique for the study of integral calculus. Once you've learned the basic antiderivatives, you must know how to use substitution when we come to more complicated integrals. So now let's consider this integral. We are asked to integrate 4x cubed times the square root of 1 plus x to the fourth dx. This is not one of our basic integrals. And there's no simple antiderivative. It's not one of our basic forms. And it's not a multiple of one of our basic forms. So the techniques that we've learned to this point in maybe Calculus 1 they just don't work here. But what I want you to notice is that, see this inside part right here? If we were to consider the chain rule that we learned in Calculus 1, notice that if g of x was 1 plus x to the fourth, its derivative, g prime of x, is 4x cubed. And notice how that derivative shows up within the integral. So now here's how the substitution idea works. If I let u, whatever u is, it's just some other variable. If I let u equal 1 plus x to the fourth, then its derivative, then du, would be 4x cubed times dx. Now let me rearrange the integral a little bit. I rearrange the integral as the square root of 1 plus x to the fourth times 4x cubed dx. And notice that what is inside the radical is what we called u, and the rest of this piece is what we've now called du. And so this integral can be rewritten as the integral of the square root of u du. And this is a simple form. Remember that I can rewrite that as the integral of u to the 1/2 du. And from our basic rules for antiderivatives, since this is just the variable to the power, I increase the power by 1 and divide by that new power. And so then this becomes u to the 3/2 over 3/2. And so that's the same as 2/3 u to the 3/2. Oh, and I really need to put a plus c in there. I forgot that in the previous step. And now we go back to our original integral. We don't want to know what the integral was in terms of u. We wanted the integral in terms of x. And so we substitute back. Well, u was 1 plus x to the fourth. And so I would write that the integral is 2/3 times the quantity 1 plus x to the fourth to the 3/2 power plus the constant from integration. And that's the substitution rule. So the substitution rule is beneficial if it looks like the integrand is the result of the chain rule from derivatives. So this is just a formal statement of what the substitution rule is. And what it's saying is, if we have these two functions that are differentiable, if the integrand of our integral, if the integrand looks like the result from the chain rule, then its antiderivative is this f of g of x, where the g of x was the inside function from the chain rule. The second statement here is how we think of that u. What an idea is, if we make the substitution, if u is that inside function of the composite function f of g of x. If u is that g of x, then du is the derivative of g of x dx. And we can make the substitution and find the antiderivative. So now we're going to go through and see some examples of the application of the chain rule. Some of them are going to be fairly straightforward, and some of them aren't. And so let's get some practice with this. All right, here we're asked to integrate y times y squared plus 6 to the 9th power dy. Now, we could integrate this by expanding that y to the 2nd plus 6 to the 9th power. If you remember how to expand that using the binomial theorem or Pascal's triangle, it would be very messy. But instead, what I'm going to notice is that if I try and let u equal, let's make a substitution. And what I see here is I have this expression raised to the 9th power. So my first idea, if I'm going to try substitution, let my substitution be sort of the inside function. So I'm going to let u equal y squared plus 6. Then du would be 2y dy. And now we look at this and say, okay, well, I notice that I've got a y and a dy, so this is good. This is going to help with the substitution. All right, so now one approach since it's not exactly 2y, it's just a y that's in the integral, one thing that you might want to do is take that statement, that du equals 2y dy, and solve it for the dy. So then dy would equal 1 over 2y times du. All right, so now let's take my integral. I'll call that I. And let's rewrite it using our substitutions. All right, so my integral is, let's see, I'd have a y times u to the 9th, and instead of dy, I'll write that as 1 over 2y du. I've replaced the dy with the 1 over 2y du. Now notice this variable y reduces out, and now I only have this constant multiple. I have this 1/2, and if you remember your rules for integration, we can bring that constant multiple in front. So my integral now is 1/2 integral u to the 9th du. And this is a simple integral. Integrating u to the 9th, I'll increase the exponent by 1 and divide by that new exponent, so dividing by 10. And so this is 1/2 times 1/10 u to the 10th plus my constant of integration. And now again, I go back to the original variable. I don't stick with u. I want to go back in terms of y, my original variable. And let's simplify this a little bit. 1/20th, and instead of u, I'll write y squared plus 6 to the 10th power plus my constant of integration. Let's try another one here. Here we have the integral of e to the 7x dx. Now, I remember from Calculus 1 that the integral of e to the x dx, I remember that that's simply e to the x plus c. Now, the issue is it's not an e to the x, it's an e to the 7x. So let's replace that 7x with our substitution. I will let u equal 7x. Then du is 7 dx. And then dx would be 1/7 du. And so then my integral becomes the integral of e to the u times, and instead of dx, 1/7 du. Again, I can bring that 1/7 out in front of the integral as it's a constant. The integral of e to the u du is e to the u, and then plus a constant. And then I'll replace the u with what we used for the substitution. And so I'd have 1/7 e to the 7x plus a constant. All right, so here's a couple more. Why don't you take a moment and try these on your own before I do them? All right, so for my first integral here, I have the integral of dm over 3m minus 7, and that sort of looks like 1 over the variable. All right, so to me, this looks like the integral of 1 over x dx. And I recall that that's the same as the natural log of absolute x plus a constant. I remember that from my Calculus 1 course. It sort of looks like that, so let's make the substitution. We'll let u equal 3m minus 7, then du is 3 dm, which means that dm is 1/3 du. All right, so now let's take that integral and replace it with our substitutions. The dm is 1/3 du, and I have now a u in the denominator. Again, I can bring that constant out front, so that's 1/3 integral 1 over u du. I know how to find that antiderivative, so that's 1/3 natural log absolute u plus a constant, and then make the replacement. 1/3 natural log absolute 3m minus 7 plus the constant. Now for this next example, the inside function isn't as obvious. But what I'll remember is I know that the derivative of sine x with respect to x is cosine x. And I also remember that this notation, right, the notation here, this sine 4th beta, I remember that that's the same as sine beta and raising that whole thing to the 4th power. Right? That's notation. We have to remember that from trigonometry. So I have the sine beta to the 4th power. And now I sort of see what my inside function is. So I think the appropriate substitution is to let u equal sine beta, then du would be cosine beta d beta. And now look, everything lines up perfectly. And my integral can be thought of as the integral of u to the 4th power du. This is a simple integral. That would be 1/5 u to the 5th plus the constant from integration, and we'll substitute back. That's 1/5 sine beta to the 5th plus a constant. And we usually use the standard notation for functions like this, 1/5 sine 5th beta plus the constant. In Calculus 1, we learned how to find the derivatives and antiderivatives for sine and cosine, and the derivatives for all of the other functions. So now let's talk about how to find the antiderivatives for, say, the tangent and the secant functions. And I use theta here, but we could have used any variable. It's not too important here. The antiderivative. So what's the integral of tangent theta d theta? Well, it's not obvious, but what I remember from trigonometry is that I can think of the tangent of theta as the sine of theta over the cosine of theta. And I still have that d theta. And now I'm going to make a substitution for the cosine. So now I'm going to let u equal cosine theta, then du would then equal negative sine theta d theta. And so notice I have a sine theta d theta, and so something it's going to work out nicely. And so that's the same as then d theta would be equal to negative 1 over sine theta du. And so if we think of the integral now with our substitutions, then our integral is the integral of sine theta over u times negative 1 over sine theta du. The sine thetas reduce out, and I can bring that negative to the outside of the integral, and so I'd have negative integral 1 over u du. Again, this is we've seen this integral, this antiderivative, a couple times now, and so this is then negative natural log absolute u plus a constant, and then substituting back, remember we let u equal cosine theta, and so then my integral is negative natural log absolute cosine theta plus a constant. And so this is something you probably want to memorize. The integral of tangent theta, or it doesn't matter what variable, the integral of tangent x dx is equal to negative natural log absolute cosine x plus a constant. Using a similar idea, we can show that the integral of the cotangent of x dx is equal to the natural log of absolute sine x plus a constant. We won't prove that one, but it's not too difficult to show. Now, to find the antiderivative of the secant function, we have to use a nasty trick. And the trick is I'm going to multiply by an interesting quantity, and that quantity is secant theta plus tangent theta over secant theta plus tangent theta. Really, all I'm doing is I'm multiplying by the quantity 1 in this special form. But now notice what happens. Then my integral is equal to the integral of secant square theta plus secant theta tangent theta over secant theta plus tangent theta d theta. And now if you think about this, if you remember your rules for derivatives for trigonometric functions, the derivative of secant theta, the derivative of secant theta is secant theta tangent theta, and the derivative of tangent theta is secant square theta. So I'm going to make the substitution. I will let u equal secant theta plus tangent theta, then du is equal to secant theta tangent theta plus secant square theta, d theta. And so that's the entire numerator. And so then the integral becomes the integral of 1 over u du. And again, we've seen this before. The integral then is, would then be the natural log absolute u plus a constant. And so then the integral is natural log absolute secant theta plus tangent theta plus a constant. And again, this is one you probably just want to memorize. You don't want to have to recreate this one every single time you come across it. So the integral of secant theta, let's go with x now. The integral of secant x dx is the natural log of the absolute value of secant x plus tangent x, plus our constant from integration. And again, similarly, we can show that the integral of the cosecant of x dx, using a similar idea, would be negative natural log absolute cosecant x plus cotangent x plus the constant of integration. All right, so there's the antiderivatives for tangent, cotangent, secant, and cosecant. And again, it's probably a good idea to just memorize those. All right, let's look at a couple more examples. The first one here, I have the integral of dx over 9 plus 4x squared. And this might look sort of familiar. I remember from Calculus 1 that the derivative with respect to x of the arctangent function is 1 over 1 plus x squared. And this sort of looks like it. Right, so remember what that means then is the antiderivative of 1 over 1 plus x squared dx would be the arctangent x plus a constant. And this sort of looks like it. We've just got a 9 and a 4 instead of a 1, right? We want a 1 plus something squared, 1 plus x squared. So it's pretty close. All right, so here's what I'm going to do. I'm going to make this, I want that term, instead of it being a 9, I'm going to make it a 1, and to do that, I'm going to use some factoring. And so what I can think is that this is the same as, all right, this is 1 over 9 times 1, 9 times 1 plus 4/9 x squared, still dx. And now I can bring that 9, really 1/9, in front of the integral. So then this is 1/9 times the integral of 1 over 1 plus 4/9 x squared dx. And now, really, I'm where I need to be, because I now have 1 over 1 plus a squared quantity in the denominator. So the substitution I'm going to make is I'm going to let u equal 2/3 x. Because notice that if u is 2/3 x, then u squared is 4/9 x squared. And then du is 2/3 dx, which means then that dx is 3/2 du. So then my integral becomes 1/9. I'd now have the integral of 1 over 1 plus u squared, and instead of dx, I'd have 3/2 du. I bring that 3/2 out in front, so I'd have 1/9 times 3/2 times the integral of 1 over 1 plus u squared du. And so now that would be arctangent u, and we'll simplify these fractions. 1/3 times 9/2, that's 1/6, if I'm not mistaken. 1/6 arctangent u plus a constant, and we'll substitute back, and so that would be 1/6 arctangent of, what was my u? My u was 2/3 x plus my constant. Alright, so now would be a good time to pause and try the next one on your own, and I'll give you a hint. The hint is to remember that d by dx of the arcsine function is 1 over the square root of 1 minus x squared. Alright, so again, this would be a good time to pause and try this one out on your own. Alright, so with that hint, I can turn that around and say, okay, well then the integral of 1 over the square root of 1 minus x squared dx, well that would be the arcsine function plus the constant of integration. And then, like I did with the previous exercise, I'm going to use a similar idea. I want to make this term right here, I want that to be a 1. So what I'm going to use is a little bit of factoring. I'll rewrite this as the integral of 1 over the square root of 9 times 1 minus 4/9 x squared, still dx. Now I can break up that radical as a square root of 9 times the square root of 1 minus 4/9 x squared. And so that square root of 9 is a 3. I can bring that 3 outside the integral. And so I now have 1/3 integral 1 over the square root of 1 minus 4/9 x squared dx. I'm going to use the same exact substitution as I did in the previous exercise. Same exact substitution, because it still fits, it still works here. And so then this would become this would be 1/3 times the integral of 1 over the square root of 1 minus u squared and times 3/2 du. I'll bring that 3/2 out in front of the radical. So I'd have 1/3 times 3/2 integral 1 over the square root of 1 minus u squared du. 1/3 times 3/2 is 1/2. And we no longer have an integral. We can find the antiderivative here. That would be arcsine u plus our constant, and substitute back. And based on the previous exercises, we can actually generalize a couple of ideas, and maybe you want to memorize them. In general, the integral of 1 over a squared plus x squared dx is 1 over a arctangent of x over a plus a constant, and the integral of 1 over the square root of a squared minus x squared dx is the arcsine of x over a plus a constant. And so if you see those forms, you can think of them as basic forms and work and simply know those instead of having to work through that substitution every single time. All right, let's look at this exercise. We're asked to evaluate the integral of 9 minus x over the square root of 36 minus x squared dx. Now we look at that square root of 36 minus x squared and we're like, hey, we just talked about an arc sine. Maybe that's going to be involved, but there's these two terms in the numerator, right? We've got these two terms here. And so that causes an issue. It's not just one term. It's not just the 9. It's not just the x. And so what we can do here is I can break this up into two integrals. Because remember that 9 minus x over the square root, that denominator is really, in a sense, one term. And so I can think of that as 9 over the square root of 36 minus x squared minus x over the square root of 36 minus x squared. And so then I can rewrite my single integral as one integral. I'd have the integral of 9 over the square root of 36 minus x squared dx minus the integral of x over the square root of 36 minus x squared dx. Now, the first integral here, this one, I'll just take this kind of over here, that's the same as 9 times the integral of 1 over the square root of 36 minus x squared dx. And if you remember what I showed on the previous slide, we can see that this is going to be an arc sine with a equal to 6. So this integral is 9 times the arc sine of x over 6, or 1/6 x, however you want to think of it. Now the second integral here, notice that if I were to take the derivative of the inside, right, the derivative of 36 minus x squared, that its derivative would be a negative 2x. And see how I have that x in the numerator? That leads me to believe that I should use a substitution here. Let's let u equal 36 minus x squared. Then du is negative 2x dx, or dx is negative 1 over 2x du. And so then this integral becomes the integral of x over the square root of u times negative 1 over 2x du. The x's reduce out, and I can bring that negative 1/2 in front of the radical, the integral, excuse me. So I'd have a negative 1/2 integral 1 over the square root of u. Remember, that's the same as u to the negative 1/2 du, and this is an easy integral. So I would increase the exponent by 1 and divide by that new exponent. So I'd have negative 1/2 times u to the positive 1/2 over 1/2. The negative 1/2 divided by the 1/2, so this is negative u to the 1/2, which is negative, and u was 36 minus x squared to the 1/2. All right, so putting both of those pieces together, my original integral would be equal to 9 arc sine of x over 6 minus negative, and I'm going to rewrite that 36 minus x squared to the 1/2. I'm going to put that back in radical form, square root of 36 minus x squared. And let's remember that we need a constant of integration here, and let's just clean it up a little bit. 9 arc sine x over 6 plus the square root of 36 minus x squared plus a constant. All right, so up until now we've been looking at indefinite integrals. Let's see what happens if we need to evaluate a definite integral. All right, so consider here we have the integral from 1 to 2 of 3x e to the x squared dx. One approach is to forget the limits. Until we find the antiderivative. All right, so let's do that. Let's just think of the integral of 3x e to the x squared dx. I know how to integrate e to a power. That's fairly easy. So I'm going to make the substitution. I'm going to try and let u equal the power. I'm going to let u equal x squared. So then du would equal 2x dx. And then dx would then equal 1 over 2x du. And my integral becomes 3x e to the u times 1 over 2x dx. The x's reduce out, and I would bring the 3/2 out in front of the integral. Oh, and that should be a du, not a dx here. 3/2 e to the u du, and so then that would be 3/2 e to the u plus, well, since we're going to, e to the u plus a constant. But then we remember that if we're finding a definite integral, so now the integral from 1 to 2 of 3x e to the x squared dx, we find any antiderivative, which we just did, and we substitute the limits. And I guess I wasn't careful here. I should have substituted back. So that's 3/2 e to the x squared plus a constant. So then the integral from 1 to 2 of 3x e to the x squared dx, remember we don't need the constant of integration anymore. And so then this would be 3/2 e to the x squared from 1 to 2. We substitute the upper limit. Subtract. We substitute the lower limit. And so that would be 3/2 e to the 4th minus 3/2 e to the 1st. And so our integral is equal to that number, whatever it happens to be. So that's one approach. The second approach, approach 2, is to change the limits of integration when you substitute. So, if I make the substitution, if I let u equal x squared, with du equal to 2x dx, and dx then equal to 1 over 2x du. Same substitution as before. Now notice that if x equals 1, then u would equal 1 squared, which is 1. If x equals 2, then u would equal 2 squared, which is 4. And so then my original integral would then be equal to the integral from u equals 1 to u equals 4. And again, we would have the 3x e to the u times 1 over 2x dx, du. I made the same mistake. So notice it looks pretty much the same. I've just substituted not only in the integrand, but in the limits of integration. And so then my integral would be equal to, and now I'm not going to write the u's anymore for the limits. My integral would now be from 1 to 4. I can bring the 3/2 outside the integral, and I'd have e to the u du. And so then that would be 3/2. The antiderivative of e to the u is e to the u from 1 to 4. And so then that would be 3/2 of e to the 4th minus e to the 1st, which is equivalent to what we wrote earlier. Just think of, just factor out the 3/2 from the original expression. So there's two approaches, and they both work the same. All right, let's see another example of evaluating definite integral. And actually, this would be a good time to pause and try this one out on your own before I do it. All right, looking at this exercise, I see that that expression in quantity, that 3x plus 2, that seems like an obvious substitution to me. So let's try it out and see where it goes. All right, so I'm going to let u equal 3x plus 2. Then du would equal 3 dx. Or we can say then that dx would be 1/3 du. And if x is equal to 1, the lower bound on the integral, if x equals 1, then u would equal 3 times 1 plus 2, which is 5. And if x equals 3, the upper bound, then u would equal 3 times 3 plus 2, which is 11. So let's rewrite the integral. The integral would be from u equals 5 to u equals 11 of 1 over u squared. And instead of dx, I'll substitute that with a 1/3 du. Let's bring that 1/3 outside the integral. And I'll leave off the u equals from now on. So from 5 to 11 of u to the negative 2nd power du. The antiderivative of u to the negative 2nd would be u to the negative 1st over negative 1. So I'd have 1/3, and then I'd have u to the negative 1 over negative 1. And remember, for definite integrals, we don't need to worry about the constant of integration. And from 5 to 11. And so then that would be 1/3 times, remember that raising a number to the negative 1st power, 11 to the negative 1st power is 1/11. So I'd have negative 1/11, subtract, and now substituting the lower limit, negative 1/5. And so then that's 1/3 by negative 1/11 plus 1/5. And we know how to add fractions. Negative 1/11 plus 1/5 is 6/55. So I have 1/3 of 6/55. And so then that's 2/55. Alright, let's finish off this section with one more exercise. Here we're asked to integrate x squared plus x over the square root of x plus 1. Alright, so let's try to use the inside of that radical and see what happens. Alright, so if we let u equal x plus 1, then du is equal to dx. And we end up, after substitutions, we would have the integral of x squared plus x over the square root of u du. Now we can't evaluate this integral. It's got both x's and u, and we've written u as a function of x. This doesn't work, so we've got to do something else. And so now what I'll say is, well, if u is x plus 1, this implies then that u minus 1 is x. And so what I can do is I can take this u minus 1 and use it to replace each of these x's in the numerator of the integrand. And so then I would have the integral of u minus 1 square plus u minus 1 over the square root of u du. And now I can simplify that numerator. Let's see, u minus 1 square, that's u square minus 2u plus 1. And then I'd have a plus u and a minus 1, and that's still all over the square root of u du. And so then that numerator simplifies further. After I combine like terms, I'd have a u square minus u over the square root of u du. And I can break that up. So then that's u square over u to the 1/2 minus u over u to the 1/2 du. And so then that's the integral of u to the 3/2 minus u to the 1/2 du. And now it's relatively easy. I can integrate each of those terms, or I can find each of those simple antiderivatives. And so then I would have u to the 5/2 over 5/2 minus u to the 3/2 over 3/2 plus a constant. And let's just clean this up a little bit. I can write that as 2/5, and instead of u, x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus the constant. All right, that finishes up the section.